This is Mr. Kim again. So I am going to go over the rest of handout number 7. So have handout number 7 ready, please. Thank you. I made a video already, but it was like an hour video, so I'm trying to shorten this video. Let's work on that. I don't want you to go through the pain of watching my lecture for an hour. So let's do it. So let's see. The main gist of this intermediate value theorem was basically given the interval AB, right? So from A and B, if I have a defined value at x equals to a, f of a, and then defined value at b, f of b, and then let's assume this function is continuous from that point to that point on, right? Then, and we say, I want to see, I give some number n, right, between f of a and f of b as an output. Can I find an input in interval a and b between a and b such that f of c will give me that n? Basically, that's the basic gist of intermediate value theorem. Two conditions that we talked about was, first of all, f of x should be continuous on the interval a and b, right? So a to b, that is, and my value n equals to f of c should be between f of a and f of b. So if this n value is outside the value of f of a and f of b, then we cannot use intermediate value theorem. And here we're not actually trying to find a value, actual c. We're just talking about, this is existence theorem, where we're talking about there is a value c that satisfies this output n, or f of c. Okay, so we'll go over this first two problems here. For each of the following functions, determine if the IVT is applicable or not and state why or why not. Then, if it's applicable, find the value of c guaranteed to exist by the theorem. So I think this should be actually not that if it's applicable, find the value of c. So we are now actually finding the value of c. Okay. So if it's applicable, you're gonna basically say that state that c exists such that n equals to f of c is between f of a and f of b by IVT, intermediate value theorem. So we're not actually finding exact c value, we're just saying there is a c that exists by IVT. But there are cases where we cannot use IVT, so we'll look at those cases. Actually, the first two are cases where you cannot use it, I believe so. Let's see. All right. So we have f of x is equal to x minus 3 over x plus 2. That's a rational function on the interval -1 to 3 for f of, and then we're trying to find, figure out if there is a c, then when I take function of it, the output is equal to 2 over 3, but that should be also in the interval -1 to 3. Okay, so let's check it out. First of all, is this continuous everywhere? So f of x is not continuous everywhere because of the denominator, right? X plus 2. When is x plus 2 equal to 0? That's when this whole thing is undefined. And that is a value actually x equals to -2. So our f of x has a vertical asymptote at x equals to -2, because -2 plus 2 gives you 0. And we know f of x is not continuous I'm just gonna use this one, okay? CONT and then dot continuous at x equals to -2. Okay. Well, we're interested in the interval -1 to 3, right? So graphically speaking, this graph, by the way, applies to both 1 and 2. So graphically speaking, we're looking at this case here, right? X and Y. So we're saying we're looking at -3, 2, 1, 2, 3, 3 here, right? And then we established that there's a vertical asymptote in -2. Some of you folks might be asking, how do you know there's a vertical asymptote there? Rational function, when you look at the rational function and then when denominator is equal to 0, you either have a hole or a vertical asymptote. So we go back to what we learned about from that first lesson where we determine if there's a vertical asymptote or there's a hole. Or a fancy way of saying is non-removable discontinuity and removable discontinuity. The vertical asymptote is here, x is equal to -2. And then rational function, the characteristics of it is if there's not a vertical asymptote or a hole, everywhere else is continuous. Okay. So since we're interested in this interval, right, -1 to 3, I just told you that our rational function will be continuous everywhere except x equals to -2. So this actually tells us the first condition here, right? What was first condition? Let's write that down again. That f of x is continuous on the interval a to b, right? So is it continuous? And the answer is yes. To -1 to 3, it will be continuous. So f of x is continuous on -1 to 3. Okay. So that's a check mark. Maybe we can use our awesome IVT. Oh, I don't have definition there. Right. The second condition was not only is that important, right, that f of x is continuous on this interval AB. Also, when you look at f of a and f of b, the f of c, right, the n value should be between f of a and f of b. IVT does not work if f of c is not between those two values. So another condition, we're going to say f of c n is between f of a and f of b. Here I'm not saying f of a should be bigger than f of b or f of b should be bigger than f of a, but they should not equal to each other, and yeah, you have to find a number that is between f of a and f of b. I mean, that f of c should be between f of a and f of b. Okay, so is that the case? So let's check it out. F of -1, and then let's check out f of 3 as well. Right? And we can plot that on the graph as well. So f of -1, what does that give us? That gives us, if you substitute for it, that'd be -4. -1 plus 2 is 1, right? So -4 over 1, which gives you -4, which means it is going to be here -1, -2, -3, -4. So I have -1 and -4 right there, right? How about f of 3? F of 3 would be 3 minus 0, 3 is 0, 0 over 5, right? So it's equal to 0. which means we're talking about over here, right? And I don't know how in between function looks like. Of course, we could plot it or we could use Desmos, but we're just looking at those two endpoints and then determining if we can use IVT to see if there's just any value of X input that will give me, I mean, does it guarantee that there is a value C such that f of C is 2 over 3? And you look at this case over here, f of C is actually 2 over 3, which is, let me use a different, that'll be 1, 2, 3, 4, 5, 6, yeah. So we're saying 2 over 3, which is a little less than 1, right? It's like 0.66666, right? It looks like it's a little close to half, but that's fine. Be understanding of that. So here, we're saying this guy is, whatchamacallit, f of C equals to 2 over 3. Yeah. I could probably like draw it with this one. Let's see if this works out. I guess much better, kind of. Yep. That was painful. Okay, kind of cover. All right, so we have to think about that. But here, my y values ranges from here, right? Negative 4. This was my f of negative 1. And then my 0, here was my f of 3, right? Which is equal to 0. So it only talks about the range from negative 4 to 0 over here. And unfortunately, 2 over 3 is not between those two numbers, right? So you know that when I want to go from this guy to that guy, let's say, remember the chicken analogy? If chicken wants to go from that point to that point, this needs to cross this road at least once. Whereas if point is over here and then we're saying continuous, it doesn't necessarily have to, I mean, it could, but not necessarily. It doesn't guarantee that it needs to cross the road. And over there. Okay. Similarly here too. It could go up and down like that to approach 0 at x equals to 3. But it doesn't guarantee it. So what you're going to say over here is, before you do that, however, f of C 2 over 3 is not between f of negative 1 and f of 3. So therefore, IVT is not applicable here. F of x. Well, you know what? You don't have to write this out. Really unnecessary. Yeah, just say IVT is not applicable in this case. All right. Let's look at the number 2 case here. Same function, but different interval. Now we're looking at negative 4 to 1 here. So this is negative 3 and negative 4 and 1 there. So this time we're looking at this interval. Negative 4 to 1. Okay. Already have a bad feeling because of the do you see there's a vertical asymptote inside this interval, which will be a big break in terms of our function, even though we don't know how it looks like exactly. So here, we already know that f of x has a vertical asymptote at -2, and f of x is not continuous at x equals to -2. It's not defined, and limit doesn't exist. And of course, the function value does not equal to limit value, right? It fails in so many different levels of in terms of continuity checkup, right? So here, we already know our number one here is going to be f of x is not continuous on interval -4 to 1. We can say why? Because f of x is not continuous at x equals to -2. And -2 belongs to is in the interval -4 and 1, right? The point of discontinuity, x equals to -2, or that vertical asymptote, happened to be in the interval -4 and 1. So right off the bat, we know, oh, this doesn't work. So this is really the end of the story. You can say, oh, from the first step already, it fails. So you can say IVT is not applicable right away. So you can like call it a day. But I want to go a little extra here because this is a really interesting case where actually second one is satisfied, but the first one failed. That's why IVT is not applicable. So let's look at second case, even though we know IVT is not applicable for this one. Seems like an extra work, but you get to have a little bit more understanding of it. So second case is our n, right? F of c 2/3, same value. Is it between f of a and f of b? Well, we got to check that out. So what is our a? -4 and b is equal to 1. So f of -4, right? Let's see what that value gives us. -4 will be -4 minus 7. -4 minus 3 gives you -7 over -4 plus 2 is -2. So that gives you 3.5 or 7/2, right? So that point, if I have to plot it, is going to be, where is it? 1, 2, 3, 4. So around the ballpark here, right? So if I have to say, this is my f of -4, right? Okay, and then how about f of 1? F of 1, when I substitute it, that will be -2/3. So it's around the ballpark, -0.67, right? So what we're saying is this point, when it's f of 1, it's around the ballpark here. Right. Let me just erase this interval. Maybe make it a little smaller. Yeah, so it's here. At x equals to 1, we get -2/3. So this value over here is going to be my f of 1, right? Which is -2/3. Let's just give them the value here. All right, and we want to see if our f of c, right? F of c. Remember that line that I drew, which I failed miserably, but recovered. So that f of c is equal to 2/3. So we have to see, is my f of c value that I want to look at, is that between, or point of the line of interest, is that value between f of 1 and f of -4, or f of -4 and 1? And then you see that it is, right? My lowest point is -2/3 with this guy, the interval, and then, well, I mean, oh, I shouldn't. Well, let me rephrase. Not lowest point. We don't even know if it's the lowest point actually, but the end point, let's say, right? The end point of this interval is going to be that gives you value of negative. So we're talking about this value, right? And then another endpoint gives me this value, and my f of c is actually between those two value, right? So it's different from that case where it was outside the value. Huh? So now this second case is basically satisfied, right? So you're gonna say f of c 2/3 is between f of -4 and f of 1. So you might think, Mr. Kim, so doesn't that mean my chicken over here, right? If it wants to get here, doesn't have to actually cross this guy here? That you know what? Let me try to make it a little bit. Yeah, this guy right here doesn't have to cross it at least once to get over here. Oh, I would agree. Only if this is a continuous function on this interval from -4 to 1. However, we established that it's not continuous. As a matter of fact, this function is going to look something like this. Okay, look something like this, where there's a huge disconnect right there, right? As you approach -2 from left-hand side, go to positive infinity, and then as you approach -2 from right-hand side, it will be negative infinity. And you see that there's no curve that is connecting this point and that point. So you see that in this case of discontinuity, you don't necessarily have to cross this f of c equals 2/3 in order for chicken to get here. It's like sort of flying, I guess. I don't know the analogy here. Give me something nice if you folks find it. But yeah. So what do you say in this case? You say, well, IVT is not applicable. Yep, that works. And maybe a little bit more specific, you can say that here is not applicable because it doesn't satisfy the second condition, right? And then in this case, it satisfies the second condition, but it doesn't satisfy the first condition. Right? So both of them fails, but for different reasons. Okay. And number 3 requires you to use a graphing calculator. For this one, I want you to use Desmos to work it out. And before we take a look at this problem, so p of x is equal to e to the x plus 2 times cosine of x. I want to go over some stuff here that e to the x plus 2, they'll be continuous everywhere. Continuous everywhere. You know what? Let's be a little bit more formal. Continuous for all x, a real number. And that's characteristics of exponential functions. If you look at it, you go to negative infinity and then positive infinity, you'll still get a y value everywhere, and there's no hole or particle asymptote for exponential functions. Also, cosine of x, same thing, continuous for all real numbers, x real numbers. So cosine function looks something like this, right? You folks have seen me draw this on, and this is a periodic function where it keeps going on to the negative infinity and positive infinity. So, yep, and there's no hole for this one either, or no particle asymptote whatsoever. There's few groups of that. Few more is polynomial function, like x squared plus 2x plus 3 or something like that, or something like this. So like parabola maybe, right? And this one too, there's no hole or disconnect, and it goes on and on basically, right? For all real numbers. And there's also something called a radical function. This is not continuous for all real numbers. It might look something like this, but from this interval to going on, you will see that it's continuous for those domain basically. There's no hole or jump and everything. At the end point, there's no limit. But other than that, yeah, it is continuous. But don't worry about this for now. You just know this one. So if I have continuous function times continuous function, I'm not going to go over that theorem with you, but that whatever function, you have a continuous function times continuous function, that is also a continuous function. Okay. Why is that important? Why did I talk about that? That's because that tells me P of X is continuous everywhere, right? Continuous for all X, the real number, right? So I don't even check. So this automatically tells me first condition to use the IVT. Let's see. Is it continuous on the interval negative to 1? Yeah, of course, you bet. So P of X will be continuous on interval negative 2 to 1. That's why it's important to know. I mean, I don't expect you to know all that. Even like rational function, I talked about all except the vertical asymptote and hole is always continuous. Everywhere else, that is. Those things just, you gotta look at case by case problems. I'll go over it every time so that you can get used to it. Okay. Okay, number 2. So I want to find if there exists a C such that when I take P of C, they will equal to 5 within the interval of negative 2 to 1, right? So in order to check that out, gotta satisfy that condition, right? That n should be between f of a and f of b. So that means we gotta check out P of negative 2 and P of 1. What does that mean graphically speaking is, of course, you don't have to always draw this graph. I'm just drawing it out because to give you some context, right? There's negative 2 and then 1 there, right? Because visually we can see it too. So P of negative 2, what does that give us? That'll be e to the negative 2 plus 2 times cosine of negative 2. E to the negative 2 plus 2 is with e to the 0 power times cosine of negative 2. And that will give me e to the 0 is 1. So you get cosine of negative 2. Oh, what the heck is cosine of negative 2 though, right? How do you find that? So that's where we need a graphing calculator. Or you can use a Google calculator for now. So what I'll do is, I'll show you both ways. The cosine of negative 2, if you just Google it, it will actually give me, and then make sure it's in radians, by the way. How do you know if it's radian or degree? You can check that up, right? If you're trying to find with a degree, cosine of negative 2 is cosine of negative 2 degree, whereas if you do radian, I guess I messed up here. Let's see. Okay, let's go. Cosine of negative 2. Now I'm using the degree, right? And that gives you like 0.9999, blah, 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 all that, right? Whereas if I use radian, that'd be different. Cosine of negative 2, negative 0.461, all that. Okay. If you use decimals, you can just do it like this. Cosine up, -2. Do you see that value they give you? That'd be -0.4161. So right now, time to get used to radian measure instead of degree. Okay. So cosine of -2, what was it again? Like around the ballpark. See, if you were here, I would have asked you directly and then did not really have to look it up. But I think it was -0.4161. I think around the ballpark, that is. Let's see. I did the recording, another recording, so let me check my memory if that's the correct case. Yeah, -0.4161 around the ballpark, right? Right, and then P of 1, we're saying e to the, let's see, 1 plus 2, so that will be e to the third power times cosine of 1. That will be e to the third times cosine of 1. What does that give us? Well, around the ballpark. I mean, this is the exact value, e to the third times cosine of 1. That is a number. But in calculator section of your test, you want to use calculator to estimate that if they ask you to. So I go over here again, e to the power of third, and then I do times, what is it, cosine of 1? What is it? Okay, it gives me 10.8523, right around the ballpark. Okay. So if you have those two values, and then you check out 5, right? Is 5 between -0.4161 and 10.8523? And you're like, yeah, you bet, right? So you know that P of C equals to 5 is between P of -2, which is -0.4161, and P of 1. Graphically speaking, what are we talking about? -0.4161 might be somewhere over here, right? Assuming that this is -1. And then I don't want to draw all this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. This is what happens if you don't plan ahead, right? Like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So at P of 1, you get like 10.85, which is this point right here. Okay. So I have these 2 points, right? And we're assuming that it's continuous from this point to that point in the interval -2 to 1, right? And we're basically talking about 5. 1, 2, 3, 4, 5. And this is too thick. All right, let's try that. 1, 2, 3, 4, 5. Yeah, much better. Okay, so we're saying P of C equals to 5. So within this interval, -2 to 1, are we crossing this at least once to get from this guy to that guy, right? Graphically speaking, and yes, you have to if it's continuous function. I mean, you could look really crazy. I showed you, right? Like many times and then go, but at least we know at least once you need to cross P of C is equal to 5. So there exists such value C within the interval of -2 to 1 that will give me P of C equals to 5. So you're going to say, so this is satisfied, that's satisfied, right? Then there exists, let me use this one. There exists C that is a real number, right? In interval, on the interval negative 2 and 1, right? Negative 2 to 1, such that f of, not f, p. So we're talking about p. P of c gives us 5. By intermediate value theorem. Okay, IVT. So all of this is, we're not actually finding what the c value is. We're just saying there exists such a x value on the interval negative 2 to 1 that if you find the output of that using this function will give us 5. It could be more than one value. All right. Before we move on to number 4, I want to show you how does that look like graphically. And so, of course, you don't have to use graph to prove anything if you know the IVT, but visual always helps. So here, I already graphed this out, e to the x plus 2 times cosine of x, which was the equation of the function for number 3, right? Yeah. And here, you see how I created a table? How do you create a table again? In case you folks want to learn that again. That will be like something like this. Let me just erase this guy again. Let's see. Yeah, on the blank, you can do y is equal to e to the x plus 2 times cosine x, which was the graph that we're looking at. And if you edit the list and then convert to table, whoo, awesome. Now you can have a table right there. And then for x value equal to negative 2, here do you see that negative 0.4161? Okay. That's what I have over here. Okay. Maybe I don't care about the other values, but I care about, what do I care about? I care about 1, right? So I'm talking about this 2 endpoints because we're talking about the interval from negative 2 to 1, right? And then you see that increasing function only looks like it will cross 5 only once. Let's see. That's why I graphed the y equals to 5, right? And then, okay, there's only one intersection that I see, which is around the ballpark. Do you folks see that? Negative 0.43. So C value is around negative 0.43 if we really have to find it. But intermediate value theorem is not interested in finding that value, like exact value necessary. It's just, is there a value within the boundary of or interval of negative 1 to, negative 2 to 1, negative 2. Yeah, I'm not tripping, right? Negative 2 to 1, that will give me output of 5 in this function. And yes, that is true. It's evidently shown by looking at actual graph here too. For intermediate value theorem, you don't really have to look at the graph. You only have to find this endpoints of the interval and negative 2 and 1. And then if this P of C happens to be between those two values, then you're good, basically. So when you're actually applying this one, it's really not going to be time consuming from now on. But why did it take so much time for us to, or me to explain it? Because we're going over the concept. So let's try number 4 here. All right, so can I use IVT here? So first of all, my idea goes like, oh, okay, is this continuous on negative 1 and 1? I look at this function. This is actually a rational function. I know there's a vertical asymptote at x equals to 2 because 2 minus 2 gives you 0. So it is not continuous. Where? Continuous at x equals to 2. But everywhere else it is continuous. Okay, so that means my interval negative 1 to 1 actually doesn't include x equals to 2 as a vertical asymptote, similar to with this case, right? Number 2. Oh, no, sorry, number one. Yeah. So here our interval is so we can say that our f of x is continuous in this case. Let me use a different. So f of x, AA. It's not working. All right, cool. So we know that f of x is continuous on the interval -1 to 1. Okay. And then second of all, I gotta check out if my f of c equals -1/2 is between f of -1 and f of 1, right? So I gotta find f of -1. I gotta find f of 1. What's f of -1? -1 over -1 minus 2. -1 over -3, which gives me 1/3. Okay, so I got one value there. F of 1 will be 1 over 1 minus 2, which is 1 over -1. Gives me -1 right there. So my -1/2, is it between 1/3 and -1? And yes, it is, right? Because -half is greater than -1, but then less than 1/3. Right? So you see that f of c equals -1 is between f of -1 and f of 1, right? So it's perfect condition for using IVT here. So that means, based on this, I can say that there exists some number c, okay, which is a real number. There exists c, at least one c, that is, there's a real number on the interval -1 to 1, such that f of c is equal to -1/2 by IVT. Cool, right? Cool beans. So, graphically speaking, what does that mean is basically, again, you have a case where, and you don't really have to rely on graph after you get really used to this IVT. And then -1, when it was -1, it was 1/3, right? So let me say this is 1. So 1/3 is like here. Okay. And then when it's 1, it was -1 over here. And we were talking about -1/2, right? Which is going through here. F of c -1/2. It is between these two y values, right? This is my, let's see, f of -1 value. This is my f of 1 value. And do you see the green? I shouldn't say green, actually. F of c value, -1/2, is between those two values, right? And plus that, it is continuous. So at a certain point, it needs to go across. You need to pass f of c equals -1/2. It could be more than once. The simplest case, it would be like something like this, right? And this point is where it will give you -1/2. And my c value, if I have to find it, that will be my c value over there. It's between -1 and 1. Okay. All right, that's all there is to it. It's just existence theorem, that there exists something that satisfies this condition that is given. All right, number 5, I want you to try it out. It could be a little tough, but I'll make a video of it, the separate video of number 5, and then show it to you as well. But I think this is a good basic ground to start off from, right? And number 5, just to let you know, I think I didn't already got number 5 down. And then, what did I say? Yeah, this one, you're going to say there exists. So you can use IBT for number 5. So just to give you some idea, you can use IBT for number 5. So that's one hint that I give you. I already gave you an answer, but how do you prove that, right? Using IBT. So impress me, folks. And yeah, feel free to use the Desmos calculator, right, to work it out. That will really help you out completing the assignment. If you have any question, let me know. Have a great weekend. See you later, folks.